This presentation explores the fundamental concepts of Geographic Information Systems, GIS, and its revolutionary impact on civil engineering practices. Through detailed examination of spatial data management, integration with other technologies, and real-world applications, this video provides a comprehensive introduction to how GIS is transforming the civil engineering landscape. Hello everyone, welcome to our first session on Geographic Information Systems and their transformative role in civil engineering. I'm Bibas, and today I'll be guiding you through the fascinating world of GIS and how it's revolutionizing the way we approach the civil engineering projects. Before we dive in, let me ask you a question. Have you ever wondered how engineers manage to integrate complex geographical data into their designs? Or how they predict environmental impact with large infrastructure projects? Well, the answer largely lies in the Geographical Information System, or GIS. GIS is not just a technology, it's a powerful analytical framework that allows civil engineers to visualize, analyze, and interpret data to understand the relationships, patterns, and trends in the geographical context. It's like having an extra vision that lets you see beyond the surface of the Earth and understand how different spatial elements interact with each other. Today's session will lay the groundwork for understanding GIS application in civil engineering. We'll explore the core concepts, examine key applications, and discuss how GIS integration is reshaping the traditional engineering practices. So let's get started. So at its core, Geographic Information Systems, or GIS, is a framework for gathering, managing, analyzing, and visualizing data related to position on Earth's surface. But what does that really mean? So think of GIS as a multi-layered digital map that combines various layers of information from topography and soil types to infrastructure networks and population densities. It's the technological equivalent of overlaying multiple transparent maps on top of each other to see how different factors relate spatially. This is displayed on the image on the right, which will be used throughout this video as it is the core concept of the modern GIS. GIS works by incorporating three key elements: the geographic location, or where things are, the attributes, what things are, like, and sometimes time, when things change. So by integrating these elements, GIS provides a dynamic and comprehensive picture of our world. So what makes GIS truly powerful is its ability to transform raw data into actionable insights. It's not just about creating pretty images, it's about spatial analysis that reveals the patterns and relationship that might otherwise remain hidden. So let me demonstrate this with a simple example. Imagine you are tasked with selecting a site for a new bridge. With GIS, you can overlay the data on soil conditions, flood zones, existing infrastructure, traffic patterns, and environmental constraints. This integrated view helps you to identify the optimal location based on multiple criteria simultaneously. So GIS hasn't always been a staple in civil engineering. So let's take a quick journey through its evolution. Traditional civil engineers relied heavily on paper maps, physical surveys, and manual calculations. Engineers would spend countless hours working with separate data sets, often facing a lot of challenges in integrating those diverse information sources. The digital revolution changed all that. As computing power increased and software became more sophisticated, GIS emerged as a game changer. Engineers could suddenly integrate, visualize, and analyze vast amount of spatial data with unprecedented efficiency. Today, GIS evolved from a simple mapping tool to a comprehensive decision support system. So modern GIS platforms offer powerful and analytical capabilities: 3D visualization, real-time data integration, as well as some seamless collaboration features that the traditional methods do not have. So this evolution has fundamentally transformed on how civil engineers approach planning, design, construction, and maintenance of the infrastructure projects. What's particularly exciting is how GIS continues to evolve with the emerging technologies. It can be integrated with building information modeling, or BIM, remote sensing, artificial intelligence, and Internet of Things. And all of these are opening new frontiers in civil engineering applications. So now that we understand what GIS is and how it has evolved, let's explore its core components. Understanding these elements is crucial for anyone looking to harness the power of GIS in civil engineering applications. So GIS works with two fundamental types of spatial data, vector and raster. So vector data represents features as a discrete points, lines, and polygons. Think of mapping a city's road, which are lines, or buildings, which are polygons, or utility poles, which are points. So vector data is the ideal for representing well-defined features with precise boundaries and locations. It's particularly useful in civil engineering for infrastructure mapping, property boundaries, and network analysis. So raster data, on the other hand, divides the space into the grids or cells or pixels, each cell containing a unique value. So this is perfect for representing continuously varying phenomena like elevation, rainfall, or soil characteristics. Raster data gives us those beautiful heat maps showing elevation changes or population density across an area and so on. So in civil engineering project, we work with both types more often. For example, when designing a highway, we might use a vector data to define the road alignment and raster data to analyze the underlying terrain and soil conditions. So one of the fascinating challenges in GIS is that we are representing our spherical Earth on flat displays and maps. So this is where the coordinate systems and map projections come into play. Coordinate systems provide the framework for defining real locations in digital space. The most common thing is latitude and longitude, which forms a grid around our globe. But civil engineers often work with projected coordinate systems, which convert locations from curved surface of the Earth into a flat plane. So the choice of projection matters significantly in civil engineering. Different projections preserve different properties. Some maintain accurate shapes, others preserve areas, while others focus on accurate distances. Say for a road project spanning hundreds of kilometers, using the wrong projection could lead to significant errors. For local projects, engineers often use local coordinate systems that minimize the distortion in the specific project area. Understanding these systems is essential for accurate spatial analysis and design. So let's talk about the tools that make the GIS work. So there's a wide range of GIS software available, from comprehensive commercial platforms to specialized open source solutions. ArcGIS, developed by Esri, is perhaps the most widely used commercial GIS platform. It offers a comprehensive suite of tools for data management, analysis, and visualization. Its extensive capabilities make it a favorite in professional engineering environment. And again, the other QGIS is the leading open source alternative. It provides a powerful functionality without licensing costs, making it increasingly popular among academic institutions and smaller engineering firms. This open source nature means a global community is constantly improving and expanding its capabilities. So besides these main platforms, specialized GIS tools exist for specific civil engineering applications. For instance, there are dedicated solutions for hydrological modeling, transportation network analysis, and infrastructure asset management. The choice of the platform often depends on the project requirement, budget constraint, and the integration needs with the other engineering software. So many engineering firms use multiple GIS tools, selecting the best option for each specific task. Now let's explore GIS. Now let's explore how GIS is applied across various domains of civil engineering. This is where theory meets practice and where the transformative power of GIS becomes more evident. So we have listed some of the few key areas like in structural engineering, environmental impact assessment, transportation engineering, and general data collection. So in structural engineering, GIS serves as a powerful tool for site analysis, design optimization, and structural integrity assessment. GIS allows engineers to incorporate multiple layers of material data and historical information into their designs. By combining 3D GIS maps with standard methodologies, engineers can learn from the past success and failures, leading to more resilient structures. One of the most significant advantages of GIS in structural engineering is the ability to visualize designs in the geographical context. Instead of reviewing designs in isolation, engineers can now see how the structures interact with the surrounding environment. and their nearby infrastructures as well as the communities. The contextual understanding helps to identify the potential conflicts and the opportunities in the early design phase. So for example, when you're designing the bridge, GIS can integrate the data on, let's say, river flow pattern, soil condition, nearby infrastructure, and traffic demands. So this comprehensive view enables engineers to optimize the structural designs based on actual site conditions rather than some idealized assumptions. So GIS also plays a crucial role in monitoring existing structures. By mapping structural health monitoring data against the geographical variables, engineers can identify patterns in structural performance and proactively address the potential issues before they become critical. Civil engineering projects inevitably interact with the natural environment, and GIS has become indispensable for assessing and mitigating environmental impacts. GIS enables engineers to evaluate the potential environmental effects by overlaying project designs with environmental data layers such as sensitive ecosystem, wildlife habitats, watershed boundaries, and so on, and soil types. So this spatial analysis helps to identify the potential conflicts and opportunities for environmental enhancement. The technology excels at analyzing complex environmental processes. For instance, GIS can model how a proposed development might affect stormwater runoff patterns, soil erosion, or habitat connectivity. So these analyses inform design decisions that minimize the adverse environmental impacts. Beyond impact assessment, GIS helps in developing effective environmental management plans. By mapping monitoring locations, tracking environmental indicators, and visualizing compliance data, engineers can ensure project meets the environmental standards throughout their life cycle. So what makes GIS particularly valuable is the ability to communicate environmental information effectively to the stakeholders. Interactive maps and visualization helps non-specialists understand the potential impacts and the proposed mitigation measures, facilitating more informed public engagement and regulatory approval processes. So again, let's move to the transportation infrastructure. So transportation infrastructure is inherently geographical, making GIS an essential tool in transportation engineering. GIS supports comprehensive transportation planning by integrating data on existing networks, travel patterns, land use, demographics, and environmental constraints. The integrated view helps engineers to develop transportation system that efficiently meets mobility needs while minimizing environmental and social impacts. In route planning, GIS analyzes multiple factors simultaneously to identify the optimal alignments. Say for a new highway, GIS might evaluate terrain, soil condition, existing infrastructure, property boundaries, and environmental sensitivities to determine the most cost-effective and least disruptive route. Traffic management is another area where GIS excels. By mapping traffic count data, accident locations, and network characteristics, engineers can identify congestion hotspots and safety hazards. These insights inform targeted interventions to improve the traffic flow and safety. GIS also enhances public transportation planning, helping engineers design systems that maximize the accessibility and efficiency. By analyzing population densities, employment centers, and travel patterns, GIS can help optimize the transit routes and station locations. The integration of real-time data has taken transportation GIS to new heights. Modern systems incorporate live traffic data, public transit operations, and even weather conditions, enabling dynamic traffic management and traveler information systems. GIS and surveying have a symbolic relationship in civil engineering, with each discipline enhancing the other's capabilities. So traditional surveying provides the precise measurements needed for engineering design, while GIS offers the framework to organize, analyze, and visualize the data in a meaningful way. So when they are integrated, these disciplines create a powerful foundation for engineering decision making. Modern surveying technologies like LiDAR, light detection and ranging, and photogrammetry generate dense point clouds representing terrain and infrastructure with centimeter level accuracy. GIS systems process these massive data sets and transform them into usable 3D models for engineering applications. This integration extends to data collection workflows. Mobile GIS applications allows the surveyor to record observations with their precise locations, attach photos and notes, and synchronize with central database in real time. This streamlined approach reduces the errors and improves efficiency when compared to the traditional paper-based methods. Beyond technical integration, the combination of GIS and surveying enhances the communication between project stakeholders. Survey data presented through GIS visualization helps engineers, planners, and the public understand the existing conditions and the proposed changes in a very intuitive way. What's particularly exciting is how this integration continues to evolve. Advances in drone technologies, mobile mapping systems, and augmented realities are creating new possibilities for collecting and interacting spatial data in the field. The true potential of GIS in civil engineering emerges when it is integrated with other advanced technologies. GIS itself is just a tool. So these integrations are opening new frontiers on how we plan, design, build, and manage civil infrastructures. So some of the key integrations that we're going to discuss in this video are building information modeling with remote sensing and with real-time monitoring systems or IoT. So building information modeling, BIM, and GIS represent two complementary approaches to spatial information management in civil engineering. BIM focuses on detailed, information-rich 3D models of infrastructure assets, capturing everything from geometry to material specifications and equipment details. GIS, meanwhile, excels at representing the broader geographical context and spatial relationship. When they are integrated, these technologies create a seamless flow of information across scales. Engineers can zoom from regional planning, that is the strength of GIS, down to a detailed structural component, that is the strength of BIM, within a single environment. This multi-scale perspective enhances decision-making throughout the project lifecycle. This integration allows clash detection between design structures and existing infrastructure or the natural features. So before construction begins, engineers can effectively identify and resolve the potential conflicts between the proposed building elements and say underground utilities or adjacent structures or some other environmental constraints. Beyond design and construction, the BIM GIS integration transforms asset management practices. Infrastructure managers can assess both the detailed component information and the broader geographical context, enabling more effective maintenance planning and emergency response. While the technical challenges remain in fully integrating the systems due to different data models and standards, progress is accelerating. Major software providers are developing interoperability solutions, and standard organizations are also working toward a common framework for seamless data exchange. Remote sensing technologies have revolutionized the way how we collect spatial data for civil engineering applications, particularly when integrated with GIS. Remote sensing involves gathering data about objects or areas from a distance, typically using sensors or satellite, aircraft, or drones. So these sensors capture information across the electromagnetic spectrum, revealing features and patterns invisible to the human eye. So when they are integrated with the GIS, remote sensing data becomes a powerful resource for civil engineering. Satellite imagery provides a broad-scale view of terrain, land cover, and infrastructure networks. LiDAR generates a detailed 3D terrain model essential for precise engineering design. Thermal sensors can detect heat patterns that might indicate infrastructure issues like leaking water pipes or thermal inefficiency in buildings. So uh, what this integration is particularly valuable is the ability to monitor changes over time. By comparing remote sensing data captured at different time scales or different dates, engineers can track the construction progress, identify unauthorized development, monitor erosion, or assess damage after the natural disasters. The accessibility of remote sensing data has increased dramatically in recent years. Commercial satellite constellations now offer a daily imagery of the entire planet, while affordable drones have made the aerial data collection accessible even for small engineering projects. This democratization of remote sensing, combined with powerful GIS platforms, has expanded its application across civil engineering disciplines. The integration of GIS with real-time monitoring systems is transforming how we manage infrastructure and respond to events. Traditional GIS has largely been static, representing conditions at a specific point in time. The integration with sensors and IoT or Internet of Things devices that create dynamic GIS platform and reflect the current conditions and detect the changes as they occur. In structural engineering, sensors monitoring bridge vibration, building movement, or dam deformations can feed data directly into the GIS platforms. Engineers can visualize this measurement in spatial context, correlating structural performance with environmental conditions or some other usage patterns. So for water infrastructure, real-time GIS integration enables sophisticated management systems. We can have sensors monitoring flow rate, pressure, water quality, and pump status, and it can provide a comprehensive view of the system performance. When some anomalies occur, the spatial visualization help operators quickly identify and address issues. Also, the transportation system benefits similarly from this integration. Real-time traffic data, transit vehicle locations, and roadway condition sensors can be fed into the GIS platforms, enabling dynamic traffic management and traveler information systems. What makes this integration particularly powerful is the ability to trigger automated responses based on spatial conditions. Like geofencing capabilities and modern GIS platforms can indicate actions when monitored parameters exceed the threshold within specific areas. For example, we can automatically adjust the traffic signal when the congestion is formed at key intersections. So this is the advantage we can have integrating the real-time data with the GIS platform. While GIS offers tremendous benefits for civil engineering applications, implementing this system successfully requires addressing several practical challenges. The foundation of effective GIS implementation is high quality, well managed data. However, this presents significant challenges in civil engineering applications. Data comes from diverse sources with varying quality, formats, and standards. Integrating survey measurements, design documents, historical records, and environmental data requires a very careful attention to compatibility as well as the consistency. Establishing standardized data models and quality control procedures is very essential for the reliable analysis. Scale and accuracy considerations are particularly important in engineering applications. While GIS traditionally work with smaller scale data than the engineering designs, the convergence of these disciplines require attention to positional accuracy and the level of detail. Engineers must understand the limitations of GIS data when using it for precise design decisions. About the metadata is the information about the data itself. It plays a crucial role in quality management. So documenting the source, collection method, accuracy, and processing the history of spatial data helps engineer assess its suitability for a specific application and avoid the misinterpretation. Managing data throughout the project lifecycle presents additional challenges. As the progress of the project grows from planning to design, construction, and operation, spatial information must flow seamlessly between stages while maintaining integrity. Establishing clear workflows and version control procedures helps prevent costly errors and information loss. Despite these challenges, advancement in database technologies, cloud computing, and data standards are making GIS data management increasingly sophisticated and accessible. Modern GIS platforms offer powerful tools for organizing, validating, and maintaining spatial data throughout its lifecycle. For GIS to deliver its full potential in civil engineering, it must work seamlessly with other software systems and data sources. This interoperability remains a significant challenge in practice. Civil engineers typically use specialized software for various tasks, like CAD systems for detailed design, analysis software for structural calculations, scheduling tools for project management, and more. Each system has its own data formats and models, creating potential barriers to integration with the GIS platform. Industry standards have emerged to address these challenges. Standards like CTGML, IFC, or Industry Foundation classes and GeoJSON provide frameworks for exchanging spatial information between different systems. However, implementation varies across the software providers, and legacy systems may not support the modern standards. Web services and API or application programming interface offer another approach to interoperability. Rather than directly exchanging files, systems they develop systems that can communicate through standardized interfaces, accessing data and functionality across the platforms. This approach is gaining traction, particularly for real-time data integration. Also, there are cloud-based platforms that are increasingly addressing interoperability issues by creating the integrated environments where various tools can access common data sources. These platforms reduce the need for file conversion and manual data transfer, streamlining the workflows across various disciplines. So despite this progress, achieving seamless interoperability remains an ongoing effort requiring coordination between software vendors, standard organizations, and engineering practitioners. Organizations implementing GIS in civil engineering should consider interoperability requirements early in the planning of the technology or technology planning to avoid the costly integration issues later. The successful implementation of GIS in civil engineering depends not just on technology but on people with the skills to use it effectively. Traditional civil engineering education has historically placed limited emphasis on geospatial technologies. Many practicing engineers have had to acquire GIS skills through the professional development or on-the-job training, like me. So this knowledge gap can limit the effective utilization of GIS capabilities in engineering organizations. Developing appropriate GIS expertise requires a kind of a balanced approach. While engineers need sufficient GIS knowledge to incorporate spatial thinking into their work, organizations can also benefit from dedicated GIS specialists who can manage complex analysis and system administration. Finding the right mix of generalist and specialist depend on the need of the organization and type of the project. Educational institutions are increasingly incorporating GIS into civil engineering in their curriculum. They are trying to integrate the GIS through the courses or the program rather than treating it as an isolated entity. So it thus helps students to develop an integrated understanding of how spatial analysis enhances their problem-solving ability. Professional development pathways are also evolving to support GIS skill development among the practicing engineers. Professional associations offer specialized certificates, workshops, and research focused on geospatial applications in engineering disciplines. Online learning platforms like LinkedIn and YouTube also provide flexible options for acquiring specific GIS skills relevant to the engineering practice. The organizations implementing GIS should consider developing comprehensive training programs that address both the technical skills and the conceptual understanding. Beyond the software operation, engineers need to understand the spatial analysis principles, data quality considerations, and integration approaches to effectively leverage their work. As we conclude our exploration of GIS in civil engineering, let's look ahead to emerging trends that will shape the future in this field. The integration of artificial intelligence and machine learning, or AI and ML respectively, with GIS is poised to revolutionize the civil engineering practices. Machine learning algorithms can analyze vast amounts of spatial data to identify the patterns and relationships too complex for traditional analysis methods. For infrastructure asset management, this technique can predict maintenance needs based on patterns in inspection data, environmental conditions, usage levels, and other factors. Computer vision applications are transforming how we extract information from imagery. AI systems now can automatically identify and classify features in aerial or satellite imagery. This automated extraction dramatically accelerates the creation and updating of spatial database used in engineering projects. Predictive modeling becomes more powerful when combining AI with GIS. Engineers can develop sophisticated models that can forecast traffic patterns, fraud risks, or infrastructure performance based on historical data and current conditions. These predictions inform more resilient designs and proactive management strategies. Natural language processing is making GIS more accessible by enabling intuitive text-based interactions with the spatial data. Engineers can query complex spatial database using everyday language like we speak, rather than using very specialized query syntax, democratizing this access to the geospatial insights. While these technologies offer tremendous potential, they also raise important consideration about data privacy, algorithmic transparency, and professional responsibility. So, we civil engineers must engage thoughtfully with these innovations, harnessing their benefits while carefully managing the limitations as well as the ethical implementations implications. The evolution of mobile and cloud technologies is transforming how GIS is used in civil engineering field operations and collaborative workflows. Mobile GIS applications bring sophisticated mapping and spatial analysis capabilities directly to field personnel. Engineers and inspectors can access and update the project information on site, capturing geo-referenced observations, photos, and measurements that sync automatically with the central database. The real-time field connectivity eliminates the data transfer delays and reduces error from manual transcription. Augmented reality or AR represents the next frontier in mobile GIS for civil engineering. AR applications overlay digital information into real-world views, allowing engineers to visualize underground utilities, propose design, or hidden structural elements in their actual location. The spatial context enhances the understanding and decision making during both the design as well as the construction phases. Cloud-based GIS platforms enable unprecedented collaboration across project teams. Multiple stakeholders can access and contribute to shared geospatial resources regardless of location, ensuring everyone works with the current information. Version control and permission systems maintain data integrity while supporting collaborative workflows. The computational power of the cloud platform supports increasingly sophisticated analysis that would exceed the capabilities of local systems or like in your local PC. Engineers now can run complex simulations, process massive data sets, and generate detailed visualization without specialized local hardware, making advanced GIS applications more accessible to small and medium-sized engineering firms. As these technologies mature, we can expect increasingly seamless integration between the field and office operations, with spatial information flowing naturally throughout the project life cycles and across distributed teams. This connectivity will accelerate the decision making and improve the coordination across complex infrastructure projects. Now, GIS is becoming an essential tool in designing more sustainable infrastructure systems that balance environmental, social, and economic considerations. Climate resilience analysis represents a growing application of GIS in infrastructure planning. By modeling the climate change scenarios and their potential impacts on proposed infrastructure, engineers can design systems that withstand future conditions. GIS helps visualize the flood risks, heat island effects, sea level rise, and other climate related hazards, informing adaptation strategies that enhance long term resilience. Green infrastructure planning benefits substantially from GIS capabilities. Engineers can optimize the placement of green roofs, bioswales, permeable pavements, and other sustainable features by analyzing factors like drainage patterns, urban heat islands, and ecological connectivity. These spatially optimized systems deliver maximum environmental benefits while supporting core infrastructure function. Lifecycle assessment becomes more comprehensive when integrated with GIS. Engineers can evaluate environmental impacts throughout the infrastructure lifespan, considering geographically variable factors like materials using material sourcing distances, regional energy mixes, and local ecosystem sensitivities. This spatial dimension to lifecycle linking leads to more holistically sustainable design decisions. So community impact analysis is enhanced through GIS-based approaches that visualize how infrastructure projects affect different populations. By overlaying demographic data with project plans, engineers can identify potential environmental justice concerns, ensure more equitable access to benefits, and develop targeted mitigation strategies for adverse impacts. As sustainability considerations become more increasingly central to civil engineering practice, GIS will play a vital role in quantifying, visualizing, and optimizing the complex trade-off involved in creating a truly sustainable infrastructure system. So as we wrap up today's exploration of GIS in civil engineering, let's reflect on the key insights we covered and consider what lies ahead. Geographic information systems have evolved from simple mapping tools to sophisticated spatial analysis platforms that transforms how civil engineers approach their work. By integrating diverse data layers, enabling powerful analysis, and supporting visualization, GIS helps engineers make more informed decisions throughout the project lifecycle. The application is spread across the civil engineering disciplines, from structural and transportation engineering to environmental assessment and surveying. So, in each area, GIS provides unique capabilities that enhance the traditional engineering approaches and enable new methodologies that will be impossible without spatial analysis. So GIS is being proven an effective tool for civil engineers. The integration of GIS with emerging technologies like BIM, remote sensing, IoT, artificial intelligence, and mobile computing is creating even more powerful tools for civil engineering. These integrated approaches are breaking down the traditional silos between the disciplines, enabling more holistic approaches to infrastructure development. While challenges remain in data management, interoperability, and building professional capacity, the trajectory is clear. GIS is becoming an indispensable component of civil engineering practice, and its importance will only grow as data availability and analytical capabilities continue to expand. For students and professionals in civil engineering, developing GIS skills is increasingly essential for career success. The ability to think spatially and leverage geospatial technologies will distinguish the next generation of engineering leaders who can address complex infrastructure challenges in an increasingly interconnected world.